Hey guys, welcome back. We're going to do the day 18 examples. So we'll do 1 through 6 in this video. Let's dive in. So number 1 is oxide of copper. So what does that tell us right away? Right away it tells me I have oxygen and I have copper. And it's 88.82% copper by mass. The overall question says, what's the formula of the oxide? When we look at this 88.82%, this is a ratio, correct? And that ratio means it's 88.82 grams of copper for 100 grams of sample. So now, for every 100 grams of sample, I have 88.82 grams of copper. The best way I can think of it doing this is for step 1 in these types of empirical formula problems, because this is an empirical formula problem, is to step 1, assume we have 100 grams of sample. Does it matter if I have 100 grams? No. Chances are you wouldn't have 100 grams if you're doing this in a lab. Especially if you didn't know. You would probably not take 100 grams. You would maybe take 0.5 grams, 0.1 grams, much smaller amount. But if I assume a 100 gram sample, I have 88.82 grams of copper in my 100 gram sample. What about oxygen? Because it's just copper and oxygen. Well, if I have 100% overall, and we know 88.82% is Cu, we can do the math, and if we subtract, I get 11.18% oxygen. Right? So that means I have 11.18% O, which is the same thing as 11.18 grams of oxygen for every 100 grams of sample. So if I assume that 100 grams of sample, I can just take their percents, and 11.18% is now 11.18 grams of oxygen. All right, so the easiest way to start this out is just using their mass percents, convert those percents into a fictitious amount of grams, 100 grams, and go with it. Now I have grams in my 100 gram sample. Step 2 will be get to moles. And we know that we divide by the molar mass to get the moles. So make sure you have your periodic table. We have 63.55 grams of copper is 1 mole. And 16.00 grams of oxygen is 1 mole of oxygen. All right, and so again, how do I do this? 88.82 divided by our 63.55. I get 1.39763965. That's a lot of numbers. How many do I keep? Well, I have 4 sig figs going. So I'm going to keep 4 numbers. Which would mean I would do the 1, 3, 9, 7. I look at this. This is a 6. Since that's a 6, I round up. Right? So it's 1.398 moles. 1.398 moles of copper. And the same thing now with oxygen. 11.18 divide 16. Now, do I need to put the 0.00 in there? No. If I write 0.00, it's the same thing as having 16. So there's really no point in doing it. 0.69875. So 4 sig figs, 698. That's going to be, since it's a 5, 0.6988. Zero. Oh, don't want to use green. I want to use blue. 0.6988 moles of oxygen. So that's technically my mole ratio of copper to oxygen. we don't like this though. Why don't we like it? It's not a whole number ratio. How do I get it into a whole number ratio? Step 3, right? Step 3, we want whole number ratios. And so you divide by the smallest. And so the smallest number is 0.6988. And if we do that, I get 1 for oxygen, obviously. And what do I get for copper? So 1.398 divide 0.6988. I get 2.000. That's 2. So I get 2 for copper. So the empirical formula is going to be Cu2O, which happens to be copper 1 oxide. Now a little side note here. When we divide, you should always have a 1, but if I had a 2, like let's look at this 2 now. If that 2 would have been, right, 2.05 to 1.95, that is 2. Everybody probably agree with it. What if I'd have got 1.25 or 1.33 or 1.5, right? Those, we don't just round those, okay? Technically, 0.25 is a fourth. 0.33 is a third. 0.5 is a half. So if I have a half or a third or fourth, I have to multiply everything by the denominator, which means I multiply everything by 4 there, everything by 3, and everything by 2. That would mean I would multiply this number and this number by whatever number I had. All right, so you will have problems coming up that you will have to do that. All right, you can't just round. I have 1.33, just make it 1. It doesn't work. You have to multiply every single element there by 3. Okay, let's look at 2. Now we have a compound of boron and hydrogen, and it's 78.14% boron. First question is, what is the empirical formula of the compound? Then it gives you the molar mass of this compound is 27.7 grams per mole. And it says, what is the molecular formula? Okay. First thing, we're going to take our 78.14% boron. The rest is hydrogen. So you take your 100% minus the 78.14% that's boron, and that'll give us 21.86% hydrogen. Step 1, assume 100 grams. Right, because we have 78.14% boron, which is 78.14 grams of boron per every 100 grams of sample. So 78.14 grams of boron. And we have 21.86 grams of hydrogen. Now let's get to moles. We're going to convert to moles, so you divide by the molar mass. Molar mass of boron, 10.81 grams per mole. Hydrogen, I have 4 sig figs here, so I'm going to go 1.008 grams per mole. So normally I use 1.01 grams per mole. And most of the time it's going to work out. But right now, because I have 4 sig figs, I'm going to keep my mass as 4 sig figs. And if we do this, right, we get our 78.14 divided by 10.81. I get 7.228 moles of boron. And since I'm in the calculator, 21.86 divide 1.008, I get 21.69 moles of hydrogen. So we had 7.228 moles of boron, and we have 21.69 moles of hydrogen. Now I got my mole ratio, and you can probably see it looks like it's a 1 to 3, but let's check. So we get whole numbers, and so you divide by the smallest, and that's 7.228. So I'm going to cheat. Since this number's here, I'm just going to hit the divide key, and that gives me that answer, and divide it by 7.228. And what do we get? 3.000. That's 3. So it is 3. We get 1 for boron and 3 for hydrogen. So our empirical formula is BH3. And that's the answer to the first question. But there's a second question. It says the molar mass, so there's a molecular compound, and that happens to be 27.7 grams per mole. All right, so if you think about this, when we do chemistry, there's several techniques that you're going to use to make sure you have or you made what you think you made, or you have what you think you have. Because we can't actually look in underneath the microscope and see the individual compounds, see the individual atoms, how they're bonded and all that. We can't tell. So we would need to check this with several different techniques. One way is to do the percentage of by mass, which we're doing now, and figure out percentage of mass. Well, if we know the mass percent, we can get the ratio of boron to hydrogen, what we did. There's other techniques that we'll learn later on, maybe, about finding molar mass of a compound. So if I know the molecular mass or the molar mass of this molecule, and I know the empirical, if we remember, the empirical formula is just the lowest ratio of the molecular formula. It could be the same thing, or it could be a multiple. So my thing is, let's check. What is the molar mass of BH3? I have our 10.81 plus 3 times 1.01 to give me a molar mass of 13.84. So my empirical formula weighs 13.84 grams per mole. My molecular compound is 27.7. So now let's figure out how many empiricals make the molecular. How many empirical formulas compose the molecular formula? So if I know the molecular formula is 27.7 grams per mole, let's see how many empiricals go into it. 13.84. Let's see, how many does that happen? So if I take 27.7 divided by 13.84, looks like I get 2. So 2. So 2 empiricals make up the molecular. So I take my molecular formula, or I take my empirical formula rather, and I double it. So BH3 I don't put a 2 in front. That's not where I put it. I go B2H6, and that would be my molecular formula. Because it's 2 empiricals. Let's try number 3. Oh, zooming in on you. What is the percent mass of nitrogen in ammonium nitrate? So there you go. So what's the percent mass of nitrogen in ammonium nitrate? Well, step 1, what is the correct formula of ammonium nitrate? Ammonium, NH4 plus, nitrate, NO3 minus. So combining those, we get NH4NO3. And nitrogen, there's 2 different nitrogens. So we're looking for the percent mass of N. So N's, there's 2 N's. 2 times N is 14.01 grams per mole. All right, 2 times 14.01 plus 4 times 1.01 plus 3 times 16. All right, so what's got going on here? This is the grams of N in 1 mole of the compound. And on the bottom, this is the mass of 1 mole of compound. So if you want to break this up in different steps, you can. You don't have to. 2 times 14.01 divide. Open my parentheses up. 2 times 14.01 plus, I have 4 times 1.01 plus 3 times 16. All right, and then we're going to times that by 100 for 100%. I get, oh, I messed up there. Second enter. Ah, there we go. I missed a key. $34.998, so 35.00%. Multiply this by 100%. 35.00% nitrogen by mass. There we go. So see how easy that was for me to mess up that key? All right, and I'm using a touch. I don't know if you guys use touch calculators or not. I prefer using a hard, solid calculator. But obviously for you guys, I'm using a touch screen. And I do this all the time. So always make sure your numbers work out. All right, sometimes you need to double check. Now, number 4. What is the average mass of a single molecule of ethanol? CH3, CH2, OH. Well, let's do, we know carbon, 12.01. Hydrogen, 1.01. Oxygen, 16. There are, 2 carbons. There are 3, 5, 6 hydrogens, and 1 oxygen. So the molar mass of this thing, 12.01 times 2 plus 6 times 1.01 plus 16.00. All my numbers are good. 4608. So if I write that out bigger, 46.08 grams of CH3 CH2OH per 1 mole CH3 CH2 I'm looking for the average mass of a single molecule. Right now I'm in grams, which I want grams, but I'm in grams per mole. I don't want mole, I want molecule. Is there a way to take my grams per mole and change it into grams per molecule? Well, the answer always is going to be yes for your questions in this course. How do I do that is the question. Well, what unit am I converting? I'm trying to convert this one. The grams is good. I want moles. So that means mole has to go on top. 1 mole of CH3, CH2, Can I go from moles to molecules? Yes. What's that number? 6.022 times 10 to the 23rd molecules is a mole. So we're going to take our 4608, divide by 6. Oh, missed the divide key. Divide by 6.022 times 10 to 23rd. And I get 7.65194. So I technically have 4 sig figs, so we did it. 7.652. 7.652 times 10 to the negative 23rd grams per molecule. So that's the average mass of a single molecule of ethanol. Now, the next question asks, do all molecules have the same mass? Do all molecules of ethanol have the same mass? Well, the answer is going to be no. I mean, think about it. We found the average, right? So that doesn't mean not everything's average. And why not? One word. Isotopes. With different isotopes, they have slightly different masses. So the answer is no. Next, number 5. Sulfur here is going to react with fluorine to produce SFX. And now there's several different options for this. There's several different sulfur fluorine compounds that could exist here. So my question is, we want to know what one did we make? So we have 1.256 grams of sulfur. We have extra fluorine here. And we know we make 5.722 grams of my unknown sulfur fluoride compound. All right, well, there's something that we know called the law of conservation of mass. So that means however much fluorine react, it's going to be in here, isn't it? And all of the sulfur reacts. So if I subtract the 1.256 grams of sulfur, the rest has to be grams of fluorine, because that's what makes our unknown. 5.722 grams minus 1.256 grams. Missed the 1.256. Looks like I get 4.466. So now I know how many grams of sulfur reacted and 4.466 grams of fluorine. So instead, now it's the same problem of the empirical formulas, except I actually have my masses in the sample. So I'm not going to assume 100 grams. I don't need to do that. I actually have the individual masses. So I have 1.256 grams of sulfur, and we have 4.466 grams of fluorine. So I'm going to divide by their molar masses. So I'm starting with technically step 2 of what we did before. Right? This is why it's so important not to memorize processes. Right? Not memorize steps instead of understanding what's going on, what information I have, and how to use that information to get what I'm looking for. So I'm not translating. I'm not doing the same thing over and over again. Right? Where I have a type of empirical formula problem, I always follow the recipe. I need to know the concepts and figure things out. Sulfur's molar mass, 32.07 grams per mole. Fluorine's molar mass. Now I'm going to use F. Why I'm going to use F instead of F2? I want to know how many fluorines. So we use 19.00 grams per mole. Use the molar mass of F, right? And this is because we want how many F's reacted, not how many F2s. All right, we're looking for F's only. Okay, otherwise I'll be off. All right, by half the amount. So 1.256 grams of sulfur divided by 32. So I'm going to take my 1.256 grams sulfur divided by 32.07 grams per mole. I get 0.03916 moles. And for fluorine, I take our 4.466 grams divided by 19 grams per mole. I get 0.2351 moles. Let's write those down. 0.03916 moles of sulfur and 0.2351 moles of fluorine. Now we're going to divide by the smallest, which happens to be 0.03916 moles for sulfur. And we're going to get 1 for sulfur. What are we going to get for fluorine? Well, some of you guys might guess if I did it to 1 sig fig, that's 4 and 24. So I should get 6. Let's look. So divided by 0.03916. I get 6. Perfect. So my answer then is sulfur hexafluoride SF6. One more. Number 6. A compound was analyzed and found to contain 53.3% carbon, 11.19% hydrogen, and 35.51% oxygen by mass. The molar mass was determined to be 90. We have 2 questions. What's the empirical formula and what is the molecular formula? All right, so we're back to percentages. And so all those percentages, 53.3% carbon or 53.30 grams of carbon in 100 grams, and 11.19 grams of hydrogen in 100 grams, and 35.51 grams of oxygen in 100 grams. Then we're just going to divide by the molar mass. All right, to get the moles. I don't want to go to moles. So carbon is 12.01 grams per mole. Hydrogen, 1.008 grams per mole. And oxygen is 16 grams per mole. Okay, so we take 53.3, divide 12.01. I get 4.438. I take 11.19, divide 1.008, and we get 11.10. And then we take 35.51, divide 16. I get 2.219. Writing this out, we have 4.438 moles of carbon. We get 11.10 moles of hydrogen, and we get 2.219 moles of oxygen. Now we divide by the smallest, which happens to be oxygen, 2.219. So that should be a 1, obviously. And so let's go back to our calculator. 4.438 divide 2.219. I get 2. Perfectly. That's great. I take my 11.10, divide 2.219, and we get 5, which is pretty close to 5. So we'll do it 5. So 2 and 5. So the empirical C2H5O. Now all we know about the molecular here is that it approximately weighs 90 grams per mole. My empirical, well, I have carbon, which is 12, so 2 times 12 plus 1 times 5 plus 16. Well, 2 times 12 is 24, plus 5 is 29, plus 16 would be about 45 grams per mole, right? And so 90 divided by 45 looks like that is 2. So we double the empirical formula. So that means it would be C4H10O2. So we have our empirical and our molecular formulas. There's the empirical, there's the molecular. And that concludes 1 through 6. We'll pick up with 7 in the next one. Have a great day. Let me know if you have any questions.